Udah dicoba belum Pak Muhtar? Belum ada yang masuk nih di email.
Langsung ke Pak Riki nih.
Oh ya, Bu Emil ini lagi dicoba Bu Emil. Oh, langsung masuk ke YouTube Bu Emil.
Langsung,
Udah
oke,
langsung
siap, siap. Siap, aman atau aman?
Oh,
Aman, Bu Emil?
itu tuh, YouTube-nya udah mulai bisa tuh. Udah,
Ya, siap, aman, aman.
hmm.
oke.
YouTube udah
Ya,
streaming ya Pak ya?
Udah,
YouTube-nya udah bisa Pak.
oke,
Oke,
sip.
sip.
Udah.
Sip, sip.
Mantap.
Langsung, udah.
Paling tinggal nunggu Pak Kapus sama Pak Dokter Aurel
Iya,
ya.
iya. Udah. Ini Pak Kapus sedang saya reminder.
Ini tidak apa-apa. Kondisi live stream aja ini sekarang.
Dari sekarang
Ya, ini udah live stream sih ini.
udah live ini.
Ya, ini udah udah live ya.
Yap.
Bu Kristanti, punten, ini nanti introduction-nya gimana ya rencananya?
Biasa aja sih Pak, ya kayak selamat pagi, selamat datang di PRIMA'sTalk. Terus udah gitu, eh, ya yang terhormat Pak Kapus, pembicara dan Pak Yuda, kemudian susunan acara, terus kemudian eh, apa? Rules of Conduct webinar Indonesia Raya, sambutan Pak Albert.
Oke. Kalau
Terus saya kasih ke Pak Yuda.
narsumnya nggak perlu di intro sama Bu Kristanti ya?
Itu nanti kan saya kasih ke Pak Yuda.
Oh
Pak
iya, iya,
Yuda
sama
yang
saya aja.
membacakan CV-nya narsum, Pak.
Iya.
Pak Yuda yang membacakan CV-nya narsum. Pak Yuda. Ladies and gentlemen, we are now in the opening ceremony. As our first agenda, it's honor for me to invite the head of Research Center for Climate Atmosphere BRIN, Bapak Dr. Albertus Sulaiman SSI MSI, to deliver some welcome remarks and open today's webinar officially. To Pak Albertus, the time is yours.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good morning, guten Morgen for everyone. Today, we have the webinar that's the title is High Resolution Climate Change Projection for Singapore and wider Southeast Asia region in support for the climate impact and surrounding. Yeah, this is we have thank you very much. Welcome to Dr. Aurel Moise from Deputy Director of Center of Climate Research in Singapore. And the topic is very useful for us, especially we get more and more climate change, and the climate change make the intensity of bad weather increase. So including bad turbulence, yeah, it's make me apa ya, malas naik terbang. Okay, and so with this seminar, I think in the near future we can collaborate to make more understanding about the climate change and climate projection better. So it can be used for us to make some adaptation for climate change. Thank you very much. Enjoy your seminar. Kita kembalikan ke MC, please.
Okay, we would like to
Terima kasih.
express our gratitude to Pak Albert for the welcome and the opening remarks. Ladies and gentlemen, before we begin our main agenda, now we will be taking a picture together. So please, sir and madam, please activate your camera and video function on your Zoom meeting. And I would like to invite the IT team to assist in taking a picture. We have... Okay, we have 3 pages. For the first page, 1, 2, 3. Don't forget to give your best smile. For the second page, 1, 2, 3. And for the last page, 1, 2, 3. Thank you, everyone. I think we are finished in taking a picture. Now, ladies and gentlemen, we are now in our main agenda of the webinar. But before that, I would like to remind all participants about the discussion session guide. If you have any question, please type your brief question in the chat box. And you may also ask by activating the raise hand feature on your Zoom meeting and until the moderators invite you to. And due to the time constraints, the moderator will present only selected questions to the speakers during the discussion session. Ladies and gentlemen, I believe today will be a fruitful day because we have Dr. Aurel Moise as the speakers. And for the presentation and discussion session will be presented over by Bapak Yuda Setiawan Jamil, PhD, as the moderator. To Pak Yuda, I leave this session to you and you may take the floor.
All right, thank you, Bu Tanti, Pak Sulaiman, everyone. Assalamualaikum warahmatullahi wabarakatuh. Good morning. We are back in PRIMA'sTalk with me again, Yuda Setiawan Jamil. I'm a researcher from BRIN. And as usual, we will be listening to a talk about climate change. So previous talk, we have a special talk about CMIP and Codex and urban climate change. And today is super special because we will listen to a talk about climate change studies from Singapore, our neighboring countries. And why I think this is important because in my view, what was Singapore done is exemplify best practice on how a country actually try to handle climate change in a proper way, which means they ensure that they get the basic science correct. And what I mean by that is the V3 report that just got published by the Singapore government a few months ago. And this is not just an assessment report, but this is a full-fledged comprehensive study about climate change, focusing on Singapore. And we know by doing that, cannot escape from discussing a wider region, which is the Southeast Asia, or in geoscience, we know it as the maritime continent. And this is what going to be hear from our guest speaker today. And the report itself is published, produced, delivered by the group, the Climate Research Department from the Center for Climate Research Singapore, CCRS, led by their Deputy Director, Dr. Aurel Mois, which he is already with us right now. So Aurel, good morning.
Good morning. Good morning, everyone.
How are you, sir?
I'm very well, thank you. Really pleased to be here, and thank you very much for inviting me to present to you and everyone else in Indonesia and talk about the very big study that we finalized earlier this year after about 4 years of conducting climate change simulations analysis and talking a lot to our stakeholders in the government. And so do you want me to start sharing now the presentation?
Okay, hold on. Let me just remind a little bit. So you will have 1 hour. Then we can use the rest of the time for questions.
Yes, understood.
So,
Sure.
so you may please start.
Thank you very much. So I assume my presentation is now in full screen mode and can be seen by you. Is that correct?
Yes, correct.
Great. Okay. So I'm starting now. Thanks. So as was mentioned, I'm talking about what Singapore government commissioned a few years ago in terms of updating their national climate change projections. And because it's the third time this is being done, it's called the Singapore's third national climate change study, or in short, we say V3. And so so today I'm going to talk about the details of the study, the results, not just for Singapore, but especially for the wider Southeast Asia region, with focus on the maritime continent. Before I head into the actual presentation, I just wanted to remind everyone here on what we're talking about when we say maritime continent, climate, and what are the key climate drivers acting in the maritime continent regions that we have to investigate, to understand, and then in climate change simulations to project changes to. So this infographic aims to provide information on, for example, the way that the monsoon moves every year between the red line to the top in July in the northern hemisphere, down across the equator to somewhere along where this green turquoise line is in January in the southern hemisphere, and then back again. So there's the seasonal migration of the monsoon that affects the entire maritime continent very strongly in terms of the rainfall and rainfall extremes. But we also have impacts from climate drivers that are associated with sea surface temperature. So in the Indian Ocean, we have the different in the eastern and western Indian Ocean warm states, and this drives a pattern that impacts on rainfall across the entire maritime continent. This is called the Indian Ocean Dipole, IOD. We also have the El Niño Southern Oscillation in the Equatorial Pacific, ENSO, and you're all aware of the different warm and cold states of ENSO called La Niña and El Niño, and they very much impact rainfall across the maritime continent as well. On timescales between 2 and 5 years, they oscillate between the different states of El Nino, neutral, La Nina. But we also have shorter time scale climate drivers that impact rainfall across the region. So MJO is the acronym for the Madden-Julian oscillation, which is a system of enhanced convection, rainfall-bearing cloud systems that propagate from the Indian Ocean across the maritime continent eastwards and through the Pacific, depending how strong this system is, it can go all the way around our planet. But the key impact area is initially the maritime continent. And the MJO travels quite fast, 30 to 80 days it takes to travel. And which means that when it hits the maritime continent, it provides additional enhanced rainfall. We also have the much shorter timescale systems like the Sumatra squall lines, which typically move eastwards from somewhere west of Sumatra and especially impact the Peninsular Malaysia, Singapore, and part of Borneo. And within Borneo, we have a vortex there that is called the Borneo vortex that very much controls how some of the rainfall-bearing systems through the northeast monsoon season travels through and brings enhanced rainfall as well. So all of these different systems modulate rainfall to some extent at different timescales. And to understand how climate is changing, we have to also understand these processes and how they might change under future climate change. So what I'm going to talk today about is a quick overview of the actual downscaling project V3, the key proposition and outcomes. I do a deep dive into the results for key variables for initially quickly through what we found over Singapore and then broadly over the Southeast Asia region and specifically what we can already see for Indonesia. And then I'll talk about some of the climate change impacts, both for us, but also in the broader regions. Okay, so let's start off. So what is it we do here in Singapore when we talk about our second or third national climate change study? So as you will probably be aware of the long history of the Intergovernmental Panel on Climate Change, IPCC's assessment that happen every so often, typically every 6 to 7 years. And here is, I show a timeline of these assessments up to the most recent one, which was the IPCC 6th assessment report. And along these assessment reports, and this is to make it really clear, these are assessment reports. IPCC does not commission any research. All they do is they assess already published research. But there's actually a second cycle that is somewhat lagged in time, which is doing all the model simulation that underpins the research that then is being reported on in the IPCC assessment reports. And these simulation cycles are called CMIPs, Coupled Model Intercomparison Projects. And this is where all the big institutes in the world that run global climate models come together and agree on running the same standard set of global climate simulations. This includes the future scenario simulation, but actually there's a lot more simulations that they do as part of the CMIP exercise, addressing key science questions that are globally relevant. But for now, we just what we care about here are the scenario simulations. And so the modeling centers run their simulations, and once these simulations are finalized, the data is being shared across a global data grid that's called the Earth System Grid. And every researcher in the world who wants to analyze these simulations can do so, can write the papers, and once they're published, for a certain deadline, IPCC includes this published analysis in their assessment report. So this is sort of the cycle that works. Of course, the global modeling simulations are a very coarse resolution. So the typical resolution on average is maybe 150 by 150 kilometers, which especially for Singapore is far too coarse to provide any useful information. So therefore, countries like us, and especially some of the if you want to look closer on the islands in the maritime continent or in the Pacific Islands, you do need to run additional downscaling simulation to zoom in to much higher resolution. And so this is what we did, which means in the third National Climate Change Study, V3, we used the global climate models and the CMIP6 scenarios. And out of the standard scenarios from IPCC, we selected 3 out of the 5 to downscale our information. So here are the AR6 IPCC scenarios in terms of emissions for going forward to the year 2100, and you can see, for example, that the 2 low ones here, SSP 119 and 126, are the only 2 scenarios that would maintain the change in global average surface air temperature by the end of this century to stay below 2 or 1.5 degrees. And this would actually involve net actually below 0, so negative emissions from a certain year in the future. Now we're just about crossing 1.5 degrees globally average. So this light blue SSP 119 scenario is already gone outdated. What we did in V3 is we used actually the SSP 126 as a representative for this, taking the green road into the future, the sustainability scenario, staying below 2 degrees by the end of the century. Then we also selected the SSP 245 scenario, which is the middle of the road scenario, and to represent the worst case for the future is to take the fossil fuel development SSP 585 scenario. Those 3 are the ones we used to run our downscale simulations. So just as a quick background on what do we actually do in terms of simulating climate, both on global and regional scale? What is a global climate model? And I just want to provide just a very broad brush view on this here. The picture on the left shows you the methodology is basically to add a grid of a certain size around the planet that also extends upwards as well as horizontally in all directions. So which means in each grid cell, the key driving equations of the physics in the atmosphere and the ocean and otherwise are being solved, and the grid cells are connected and understand what is happening in neighboring grid cells. And then this climate model will then start from a certain initial state. So you give it the initial temperature, winds, and humidity. You press the start button, and all that is happening is the equations inside the modeling system and the natural forces that are being provided, like the solar radiation, but as well as the human-caused forcing, which is the greenhouse gas added to the atmosphere, the scenarios into the future. These are the key drivers for this climate model. And it moves forward for the next 100 years or 200 years, which is a very expensive process. So these large modeling centers that do run global climate models and participate in these CMIP exercises, they're spending significant amounts of resources to do so. Of course, the spatial resolution and the complexity of these global models have been increasing over time. And when they started off, the resolution was several hundred kilometers, and now it's around 150 to 100 kilometers, the spatial resolution in the atmosphere, which is still too coarse for a lot of applications. So what do we do when we say we downscale these global models? So what you start off with is you select a domain of interest. So where do you want to downscale? And so for us in V3, we selected our first domain here, which is the middle blue figure here, which is very, very similar to the Cortex Southeast Asia domain. And we ran our downscaling regional climate model inside this domain, and which took on the edges of the domain all the information relevant from the global model. So the global model keeps feeding in at the edge of the domain their information, and to run a much higher resolution climate model on the inside within the domain. So this modeling system produced data at 8 kilometer resolution across the entire domain, which is quite high for such a big domain. And so we are basically through this project produced the highest resolution climate projections information for this region shown in this domain. Now, in a second step, we chose a second domain inside, and this is shown here with the white square or blown up at the bottom here, where we used this 8 kilometer data to further downscale to 2 kilometers, and therefore have quite high resolution information, especially over Singapore at 2 kilometer resolution, but also, as you can see, over Peninsular Malaysia and Sumatra, we do have the 2 kilometer simulations available. So this is sort of the technical aspect of running this. This is we spent 3.5 years running this downscaling model on supercomputers in Singapore and Australia to conduct this study. A very significant effort on high performance computing. Just wanted to also highlight the importance of engaging our stakeholders at the very beginning as well as throughout our study. So we basically spent, before we even started the project, a lot of time on discussing stakeholder needs. What was it they're interested in? What kind of variables? What kind of spatial and temporal resolution of information they're interested in? So what were the path to impacts from this study towards the Singapore government in terms of future climate change and its impacts? And then once we started, we had two key flows. One was what I just described before, which means we selected a small number, actually 6 out of the 45 available global climate models. And this was a very extensive sub-selection process to identify what were the 6 best models to choose. But then we downscaled those 6 models to 8 kilometers for the 3 scenarios, and then used this to downscale to 2 kilometers also for the 3 scenarios over those 2 regions that I showed before. At the same time, we also produced the latest update on sea level rise projections. And I show this separate here because sea level projections are done quite differently to these other projections. First of all, the science describing how locally sea level is changing is very, very complex and involves processes that are at global scale. For example, what happens at the Antarctic or Arctic ice sheets, what happens to Greenland ice, down to regional scale. So how is the increase in temperature and impacting the key ocean flows in any region? How are these changing? And this then goes further to the local scale, where you have local impacts to sea level. For example, one of the key questions is what we call vertical land motion. So this is where the land that you stand on is either rising or sinking due to various either tectonic long-term processes, recent earthquakes, or other things like an extraction of groundwater. So this is where the land is moving underneath you, and that also, of course, changes the relative and position towards the sea level. And so the information on sea level projections through IPCC methodology was done only at a point scale, applied to the locations where in each country tide gauge data is available. So this is not maps of sea level rise in the future, but basically time series at a particular point where there is already data available from tide gauges. And I get into this a little bit later again. But this information comes in a separate pathway to the overall data visualization portal where we provide the information for everybody to use. So our project was a whole of nation effort in Singapore, where we were supported by Singapore's National Supercomputing Center, as I touched on before, that we spent a lot of time doing those simulations and analysis. And we created a large volume of data, as you can see here, about 10 petabytes, which we're just in the process of reducing now in some effective way, but this is a massive amount of data. And in this process, we were engaged with around 20 agencies in Singapore to continue to inform our process. Okay, so let's move to some results, and I'll probably go a bit more quickly through the results on Singapore, because I want to really spend more time on talking about Southeast Asia. So I mentioned before about the sea level projections are only available on tide gauge locations. And so here you can see two examples. So there's a tide gauge at the southwest end of Singapore and another one on the west coast, Sultan Shoal and West Tuas. And so here you can see projected changes in the sea level for these tide gauges for the three scenarios. So the low scenario, the medium scenario, and the high scenario in pink. Black on the left is the observed record in the history. And you can see that by 2100 we see an increase on average there, even in the high emission scenario, that's around 75 centimeters. And that's actually also very close to what the global average is. On average globally, by 2100, the increase is around 75 centimeters. When we move 50 years further to 2150, we can see that there's already some significant increase, and at the very top end of the projected change, it actually hits the 2 meter mark in terms of the changes, both for these tide gauges. So overall, we looked at 6 tide gauges in Singapore that had long enough historical record that this methodology could be applied. If we look at rainfall changes over Singapore, and this is the same story for Southeast Asia, annual averages don't reveal much. You need to really look into the various seasons, and then it reveals where there's increases and decreases in the various seasons. And I will show this later for Southeast Asia as well. So we do see some increases in some seasons, decreases in other seasons in the mean rainfall changes, but for us the key interest, as well as for the stakeholder, is what happens to extreme rainfall. So here you can see the projected changes for April, May, and October, November in extreme, so the 99th 0.9th percentile of daily rainfall events projected to the future. And you see in percent, this shows, you can see that there's some significant increases, especially for the high emission scenario SSP 585. We look at the opposite end, which means dry spell, and we looked at how the frequency and the duration of dry spells would change into the future. And here we see the end of the century projected changes for the three scenarios in terms of the dry spells. And again, we can see the picture there says it's increasing annually as well as seasonally. Just moving on to maximum and mean temperature changes in the future, and so this is a daily mean and daily maximum temperature, and we can see that compared to the observed averages, the increase could go up to 5 degrees and beyond. So this is sort of the for daily mean and maximum temperature, worst case scenario is an up to 5 degree change in the future. Now, we're all interested in how this projects to heat. And so in Singapore, we adopted the wet bulb globe temperature as a key indicator for heat stress, WBGT. And WBGT uses not just temperature, but it also takes in humidity, winds, and solar radiation, combined metric to represent a heat stress. And we see for daily mean as well as the daily maximum changes in WBGT for the future, similarly strong increases as for temperature, but not quite as large as. This is not just temperature, but also humidity, winds, and solar radiation. But what does it mean in terms of thresholds and categories for the public to be concerned or not? So in Singapore, there are thresholds on WBGT that indicate a green, yellow, or red level of heat stress, and with red being the warning, a high warning level for heat stress days. And so what we did is we converted these figures in change in WBGT in number of days where the daily maximum WBGT is equal or exceeding that threshold to be a red flag day for Singapore. And you can see that for Singapore in the future, under the high emission scenario SSP 585, even at mid-century, we could look already up to a very high number being red flag days, but by the end of the century, this is getting close to every single day. So the last one here is we also looked at winds and wind speed in future climate, and similarly to rainfall, the changes in winds are very much related to the seasonal changes of the large scale circulation, the northeast and southwest monsoon season, and the intermonsoon seasons in April and May. And you can see the winds in Singapore in generally are quite soft, as we are very close to the equator, and therefore those changes, even a change of 14%, will still keep the winds fairly soft. But these are mean wind speeds, not wind gusts. So we released all this information early in January this year, and there was a lot of media attention in Singapore on this, and we've continued to provide more information and the story around climate change in Singapore, as well as the story of future heat and sea level changes, is continued to be explored in the media. Okay, so now I want to move on to talk about the broader region, as we have this high resolution 8-kilometer simulations across a very large Southeast Asia domain, and I want to talk in similar detail through some of the results in Southeast Asia. So starting off with sea level projections. So we've seen that the sea level projections by IPCC and by us in this V3 study are done at locations of tide gauges, like this one here, and so what we did in this study is we looked around the region, where is there available data on tide gauges, and when I say available data, what I mean is that there is a global archive that is being maintained with quality control, and that global archive makes monthly tide gauge information available to any researchers, and so this is where we can access the data. This is where we then added the IPCC methodology on looking at projected changes up to 2150 in these different tide gauge locations. And so what you can see here is, and I have on the next slide, have this blown up a bit more. You can see the different locations that we looked at. So, for example, our next door neighbor in Johor Bahru, also Penang, but then we looked at Phuket, Bangkok, and also Yangon. We looked at Da Nang, 2 locations in the Philippines, and also Kota Kinabalu, and assessed the future changes for the 3 scenarios. So the 3 numbers here represent in blue the low scenario, in yellow the median scenario, and in red you see the higher scenario results. So you can see there's actually quite some interesting differences. So in Johor Bahru we see similar numbers as in Singapore. If we move to Bangkok, we can see some much stronger increases there, and similarly, for example, in Manila, and this is driven by their already historical steep subsiding of the land around that city. So we know from published data that there's been subsidence both in Bangkok and Manila, and because of that historical subsidence, the projections forward are actually producing much higher sea level projections. So when we look at temperature for Southeast Asia, this is just a map that shows by the end of this century what are the changes in surface air temperature across the region. And you can see that on average we see a range between 2 and 5.5 degrees across the region, and you can see that there are certain hotspots in Southeast Asia, in the maritime continent, where we see those higher values being hit under the high emission scenario. If you on the right hand side you see sort of the decadal, so 10-year averages between now and the end of century, how this increases very, very linearly. Now I just want to highlight that this is an annual change, annual average change by the end of the century. If we look at this seasonally, we would actually see some seasons hit the 6-degree mark in terms of areas of whereas these hotspots of surface air temperature changes, which is a very strong change. Now we move to the maximum daily temperature. So away from the mean to what is the daily maximum temperature and the changes, and we can see a similar map here, and I show this map line up in a minute to look closer over Indonesia. But so on average across the region, we see by the end of the century, basically between 2.9 and 5.4 degrees change. And this is also shown here in that sort of indicate in that red bar on the right-hand side, which is the high emission scenario by the end of the century. This right figure also then shows for the other scenario, and also the same scenarios for during the mid of the century. But the key message is hot days are going to become the norm by the end of this century. So if we zoom in just for this region, you can see actually where across the maritime continent some of these hotspot regions are in terms of daily maximum temperature changes hitting near 5 degrees. We also produced country-specific information here. You see for Indonesia, the summer wet season and winter dry season time series of daily maximum temperature changes. So you see the baseline period in gray and black, and then the 3 scenarios time series to the future, and the bold line is the average, whereas the shaded area around it provides the spread, given the fact that we had 6 different models running simulations, and they all have slightly different results in terms of future changes, future climates. So this provides then, of course, the typical bars and the range of what these changes are for the different seasons. We also have the humidity changes. So this is daily mean specific humidity changes for Indonesia in the future for both the wet and the dry season. And these are just examples of pieces of information that you can access through our visualization portal that I will show you later how to link to. If we look at what we call hot days, which are the 95th percentile, so if you put all temperatures for each days together and you draw the bell-shaped curve, you look at the top 5% basically. What are the temperatures at the top 5%, and how are these temperatures then changing? How many of hot days will we see in the future? And so here you see for the countries where we produced the analysis, that the increase in percent of hotter days for the 3 scenarios. So in blue again, the low scenario, the medium scenario in yellow, and in red is the high scenario. And I just indicated with the gray dashed line the 50%, so a 50% increase in hotter days, and you can see that there's a few countries that show an above 50% increase by the end of the century under the SSP 585 scenario, which is Brunei, Indonesia, Malaysia, and also Singapore, which of course with Singapore we are also looking in having to add an urban heat island effect to this. So specifically for Singapore, and we can do this analysis for other countries as well, is where we just looked at actually the annual cycle across the year. What are these number of very hot days in the future? And here you can see obviously there is a difference across the year, with some periods like March, April, May, and June showing much more hot days in the future, and a very strong increase, as you can see in terms of where this reaches. Now moving to heat waves, and so we looked at heat waves across Southeast Asia. At what are the changes in the frequency, the duration, and the actual intensity, the magnitude of the heat waves changes. And so overall, as a summary, we can say that there's the increase of 120 heat wave days per year on average across the entire domain, persisting for 40 days longer than in the history, and up to a 4 degrees increase in the magnitude over Southeast Asia under the high emission scenario SSP 585. So if I zoom into again the maritime continent region, so here again there's the change in frequency in days per year in the top left, the change in the length, the duration of the heat wave in days on the top right, and the change in the magnitude on the bottom left. And so a reminder that the definition of heat waves here for this analysis is that you have at least 3 consecutive days where the temperature is above that 95th percentile of the climatological temperature for any of the locations there. And the baseline period to compare this to is our standard 1995 to 2014 baseline period. So there's some really significant changes to the heat wave numbers. Moving to rainfall and looking at the projections of rainfall changes to across the region. So here I'm looking at the mean, the total rainfall change under the SSP 585 scenario in for the two maps in the bottom, and so this is the DJF wet season, December, January, February, and the June, July, August dry season. And the figure on the top right here then goes across the 3 scenarios and shows the mid-century and the end-century results for the mean changes in rainfall expressed in percent. So we can see for the wet season there's only little increase and little change. The key information we take away from this is this really strong change in the dry season that we see in our data. But similarly to what I showed before with Singapore, there's always the main interest is on the extremes. So what is the maximum daily rainfall doing in the future? And here are the similar figures for end century SSP 585 change in maximum daily rainfall, and you can see this really much stronger changes in maximum daily rainfall across the maritime, increased the wet season, and significant decreases during the dry season. So this is what we typically call RX 1 day. So what is the maximum 1 day rainfall in the season? And again, as I said before, we provide country-specific information in our portal, and so here we look at the time series of the wet season and dry season change in rainfall for only Indonesia. And so here you can see the little change in the wet season. But we do see some decreases in the dry season, which is shown here by where the mean change is moving below the dashed line. Similarly for time series on the maximum daily rainfall. So this is the looking at the RX 1 day. What is the maximum 1 day rainfall in the wet season and the dry season, and you can see the increases in the wet season on the maximum 1 day rainfall, where we've seen before the mean rainfall is actually sees little change, and whereas we see this slight decrease in rainfall for the dry season, but with large variability overall. We also analyzed what we call RX 5 days. So what is the maximum 5-day rainfall. So and across the season, and you see on the right hand side the figure for DJF, December, January, February, and then June, July, August, matching to some extent what we see for the maximum 1-day rainfall changes, which is this increase in the wet season and this slight decreases, especially in southern Sumatra and further to the east, in the June, July, August season. We had a specific look on what dry spells mean across Southeast Asia, and so we took our data and analyzed 3 key metrics here. One is basically the maximum dry spell length, which is the consecutive dry days metric. We looked at the average dry spell length and the average dry day counts, and so what we separated out were basically the 2 key seasons that separate the key information in terms of hemispheric rainfall differences, and I show this in a minute. So the seasons we look at is boreal winter, boreal summer, defined by these 6 months averages. So if we look at what the IPCC 6th assessment report says with regard to drought risks over the Southeast Asia domain, you can see there's a both with regard to vulnerability and is a very strong signal in terms of very high, and therefore a really high to very high drought risks. Now, what we see is that the prolonged dry spells basically enhances any probability of experiencing droughts. And so dry spells are building blocks of drought. So looking at dry spells was one of the first points that we analyzed. So again, so this is this difference in the 6 months seasonal total rainfall between the wet season and the dry season, and this figure here is just to emphasize how really clean and neat this cut is between the 2 seasons, using observational data for almost the last 40 years, where you could see the wet and the dry seasons. So we're using this to look at these 3 metrics, and we look at these 3 metrics separated by the 2 6-month seasons. So this one here, for example, shows the maximum dry spell length for the NDJFMA, the 6-month season, and this is the southern hemisphere wet season and the northern hemisphere dry season. And so you can see the line indicated, the red line here indicating that separation. Without focusing too much on these simple figures, just to say that what we did is we looked at the dry spells by warming level. So we basically analyzed the data by half-degree steps, starting at 1 degree, 1.5 degrees, 2 degrees, and so on to reach 5 degrees, and then provide information on what this metric will look like at these different warming levels. And so we know the 5 degree warming level is the 4.5 to 5 degree warming level is predominantly in the SSP 585 scenario, but this is these warming levels is a different way at looking at future global climate change. Instead of just going along the SSP scenario pathways, you can look at actually separate distinct warming levels. And this is what we did here. So the key message here is this season is the southern hemisphere wet season, and you see in red colors here with increasing warming level a stronger and stronger increase in the maximum dry spell length, even in the wet season, southern hemisphere wet season. If we look at the dry season, so this is the southern hemisphere dry season, this increase is even stronger, as you can see in these figures down here. So the extreme dry spell events get longer during the southern hemisphere dry season. Now here we look at these average dry spell length, and this, of course, being average, is the change is somewhat softer, but still matches the picture that we saw before, that we have an increasing trend in the length, even in the southern hemisphere wet season, which is very strongly enhanced, this change during the southern hemisphere dry season. So this is the average length of future dry spells in the southern hemisphere dry season. The last metric we looked at is the dry day count. So and basically what we see here is for the wet season, drier conditions during the wet season as well. We see also drier conditions in the northern hemisphere dry season, but quite pronounced in the southern hemisphere, and that picture is then much stronger enhanced for a southern hemisphere dry season, again with many more dry day counts. So what we want to do here is to just summarize this specifically for Indonesia. So this is basically the 5-degree map as was in one of the previous slides, and we then for each of the different warming levels show here what is that change in the maximum dry spell length just for Indonesia. So you can see this sort of soft increase in the mean, but strong increase in the range of the change in future length of maximum dry spells. And similarly for the dry season, and we can see this is more pronounced for Indonesia. Now we know that that the biomass burning regions across the maritime continent are typically focused in some key regions, which are shown on this map. And so if I overlap the changes in the future dry spells duration and length and number, so there's actually a very close match with where this is. So the takeaway message here is that our results suggest quite a strong potential for increase burning and haze effects in the future. So I'm moving towards the end of my presentation, and I wanted to talk about what do you do with these results in terms of analyzing and assessing climate change impacts, and what do we do and what could be done. So climate change impacts. So as I said, we produced 8-kilometer resolution data in this really large domain over Southeast Asia and the maritime continent, and 2-kilometer data over this smaller region, still encompassing significant areas, including our Singapore. And with this data, you can actually do an incredible amount of climate change impacts research and analysis in many different countries, and also for many different aspects. So for example, for us here in Singapore, we identified some sort of key climate change impact areas that we're now already moving forwards in terms of conducting research in-house in CCRS, but also awarding projects at local universities looking into this. So whether that's biodiversity, energy, food security, vector-borne diseases, the impact of heat on human health, or are the key areas that we're already being active in. So as an example, Singapore food security, as Singapore imports over 90% of its food, the climate change impacts on source countries is of great interest. So here's an example as Singapore imports rice from Thailand, Vietnam, and Indonesia. We started to analyze the impact of temperature thresholds and its changes under future climate to this cycle of growing rice in key areas in Thailand. Since we have this high resolution 8-kilometer data, we can go all the way down into district level and look at where are the key rice production areas and what is being produced, and we look at these districts and use key metrics, for example, exceeding 35 degrees, or how many 3 or more consecutive dry days, which are all impacting rice during its planting phase, the growth phase, and harvesting phase. And we can provide information, and we already do so, on how many days are being impacted in terms of crossing the threshold. So this is an advanced study. We already analyzed data for Vietnam, and we're just about to start to analyze data for Indonesia. We're very interested in actually collaborating with anyone who is interested in this issue. Another topic is vector-borne disease, especially dengue, and so this is a simple study that we're doing with one of our universities in Singapore on looking at the climate-only dengue sustainability of the mosquitoes in Southeast Asia. So this is not looking at how many cases there are. This is just looking at the climatological sustainability of say Aedes aegypti across Southeast Asia now and in the future. There's two key other areas that we are active in. So first of all, as heat is becoming a very important message coming out of our study for Singapore, we actually conducted more urban climate change study. As for Singapore, we need to understand the added local warming through the urban heat island effect. So we're currently running already a 100-meter urban model forced by our 2-kilometer V3 data to understand what is the urban heat island impact on Singapore in the future. We're also testing a mitigation scenario as part of this, and so of course one of the key pieces of information is our V3 data provides the future climate, but we also need to understand what's the future urban morphology. How is the city changing in the future, to understand what future heat will urban heat island effect will be like. Connected to this is heat stress and heat waves. So we use, as I said, the WBGT, the wet bulb global temperature, as a measure for heat stress, and we have an observational network of WBGT measurements, and we're also looking at various heat wave definitions to really understand the impact of heat stress for Singapore. So as I said just before, I want to use this opportunity to talk to you, to emphasize, to get in touch with us, with me or us, CCRS, if you want to not only access data, but especially collaborate on climate change in the region, but also climate change impacts. a few more slides to go. There's one slide on science communication, which is a huge part of the study that we took, and where we continue to invest significant effort and time, is to communicate our science to stakeholders, to agencies, to industry, to university. And so throughout this process of conducting the study, we've done briefings to all levels of governments, all the way up to the very top. We had this very successful launch event where the minister was there, and she launched our study results. We had many media engagements. We did a lot of brochures and videos. We have a technical report, a stakeholder report, and a data visualization portal that where everything comes together, and you can access all of the information that I walked you through, and including a one-page V3 on a page infographic. So here are the stakeholder reports and the science report, and just a quick view on the visualization portal. We have a QR code for anybody to access the data visualization portal. It's open and free to the world to investigate all the results that we produce. And I just wanted to show you a quick couple of slides on the visualization portal. First of all, all of our reports are on the portal and brochures, but also the portal is mobile friendly, so you can also run it on your phone. And we show on this portal all the different visuals for not just Singapore, but also for the region. As you can see here, some of the figures that I showed you there are here as well. And we have what we call V3 on a page, which is our infographic that summarizes the what we call the key results on basically temperature, heat, rainfall, and sea level for us. Here are the QR codes for not just the V3 portal that I just described, but also if you want to follow us on LinkedIn, CCRS, or if you want to explore some of the educational videos on the different climate and weather drivers and events. Yeah, the MSS YouTube channel has a series of now, I think, 11 or 12 of those videos, which are really nice. And with this, I end my presentation. Thank you very much. I hope this was of interest and useful to me, and I'm happy to take any questions. Thank you.
All right, thank you, Aurel. Very exciting studies, very exciting results. Let's go to the Q&A session right now. And I'm sure some of us already have questions in mind, but I will use my privilege as a moderator to post the first question. So, Aurel, you show that the future, there's a drying at the southern of the maritime continent. So have you guys figured out what's the cause? Is this something to do with some shift in Hadley circulation or some dynamic causes of that? Thank you.
Yes, thanks for the call. So we're still exploring the story, what we call the storylines of the causal changes, and what would drive this. So for us, there are key changes in the circulation that we are following, and so it's probably too early to say something definite, but we're looking into the circulation at the moment to understand what are the key drivers of these changes in the future.
All right, thank you for the answer. All right, so let's give it to the floor. We have one question at the chat box in Zoom. I wonder if Aurel can see by yourself in the chat box. There's somebody.
Yes. So
the 5 models.
Yes. So I see the question, and thank you for asking this question. So first of all, how do I determine the 5 models and what I had to choose? And so we did a model evaluation exercise very extensively, where we looked at the global models in various dimensions. So one was skill, and so we analyzed the models on sort of order one's mean skill, order one. So what is the mean pattern conserved compared to the observations, and just sort of looking at mean states. Then we looked at the variability and the teleconnections inside. So we get skill information from all the models on this. But the skill of the models in representing key climate states and drivers and variability in the region is only one aspect. The other aspect was what we call model independence. So we know that the global models are all more or less related to each other. So for example, there are several models, global models that use the same ocean model, or same family ocean model, or same atmosphere model, or so there's actually, you can do a family tree of those global CMIP models. And so what we wanted is our 6 models to be as independent as possible. So that was another criteria. The other criteria is the spread in equilibrium climate sensitivity. So this is basically each model, it has a specific response to a standard increase in CO2 forcing. And so some models react very strongly to the same increase, and some models not so well. So this is what we call the hot and cold models. So if you plot equilibrium climate sensitivity and the whole model family there, you see some are really hot and some are not so hot. And we wanted our 6 models to also represent the entire range of these cold to hot models, so that we are not just looking in one end, basically. So that was the other one. The next one was if you plot a figure of what is the temperature change versus the rainfall change over the whole domain, and you plot all the global models, you see also that quite a significant spread in terms of future change in temperature and rainfall. And we wanted to make sure that our models also represent that range. We didn't just want to go to one corner in terms of rainfall and temperature change for Southeast Asia. So we wanted to make sure that that's also covered. So as I said, there's a whole range of dimensions that we assessed, and in the end we came up with a list of 6 models that provided that looked the best on this. And so I should say one additional metric here is data availability. And I don't know whether you've come across this, but CMIP 6 is different to CMIP 5, because some of the key variables that you need for downscaling are not a tier 1 like a requirement in CMIP 6 as it was in CMIP 5. So therefore, some of the data is not available. So you find a really good model like the GFDL4, that CM4 that we've looked at and looked for, and then there's no data there to actually downscale your model. There's no driving data that you can run. And so we complained to Codex about this, and they're aware of this issue. Obviously, it was a bit of a blind spot that they didn't force the global climate modeling centers to basically save and submit those fields. So my guess is Codex, based on CMIP 6, will be somewhat a reduced set of information, because not all the data is available. So that's that question. The second part is for rainfall, what indicators determine that the results of downscaling are usable? So first of all, for Singapore, and which was our number 1 priority with this study at the time when we finished it, we actually bias corrected the data so that it was useful for our stakeholder agencies to take and use it and apply it. So we actually applied the bias correction, and the comparison to historical data sets allowed us to assess, yes, indeed, that it is useful. But we also conducted a study, actually together with a collaboration with Australia, is to look at what sort of a typical added value analysis of downscaling versus global climate simulations, and especially for extreme rainfall, we see a clear added value in our downscaling simulations above the global simulations. Is it possible to get data on downscaling results? So data, yes, it is possible to get data. So we are currently building, apart from the visualization portal that I showed you, we're also building a data sharing portal, and that should be available, I think, early next year. So that's our understanding, because it's not us building it, so it's sort of a separate IT division that's building it, and so the expectation is that there'll be an automated data sharing early next year. In the meantime, we can still share data on a project basis. So if you come to us and want some data, then we'll talk to you and we'll find a way of how to share data. As the portal becomes available, we will also make large parts of the 8-kilometer data available in the Codex, under Codex Southeast Asia. So we're currently negotiating with Codex what to do, where to put it, what are the possible solutions to provide our data to Codex Southeast Asia.
All right. I think I'll answer all the questions, unless Pak Mahmud would like to follow up, probably. If not, we can continue to the next.
No, thank you very much.
Thank you.
Yeah.
Okay, thank you. Okay, let's move on to the next question. It's still in the chat box.
Yes, I can see. So
Berdasarkan.
what is needed in SSP climate projections applied in big cities such as Singapore and Jakarta? So I think I mentioned before that when you want to look at big cities, you need to understand the urban morphology and not just the climate. So what part of your city is, so you need to know the elevation. You need to know for each grid cell in the model, what is it covering? Buildings, high rise, low rise, grass, parks, forest, whatever the urban morphology is that is underneath it is important. So when you run a separate urban model, the urban morphology and how this changes in the future is really important. So because if you run the future climate with the current morphology, the understanding is that in 80 years time or 70 years time, the city looks just the same, which we know is not true. So my suggestion is to work with whatever agency that is in your country or with regard to Jakarta, to understand what are their plans for the future. I'm sure they're thinking about certain plans for the future, and then you can map those plans onto your morphology and use it in an urban model to combine with the climate. So that's what we're doing. That's the way we're going, and we're actually keen to look at other cities in Southeast Asia as well. So I know there's a project in Codex Southeast Asia that's looking at mega cities, and it would be great to work together with them. But also, if there's anybody here on this call who's conducting and interested in urban future climate, please let us know. The difference between SSP and RCP scenarios, I guess there's some difference, but not very much difference between SSP and RCP. And if we compare our projections with the projections last time around, we see somewhat higher temperatures. So as I said, hitting and sort of going beyond the 5-degree temperature change mark is a first. We didn't see this in 7 years ago or 8 years ago when we looked at with the RCPs. So that's definitely, but it's it's not a huge change. I mean, whether you stay at 4.6 or 5.3, this is that kind of difference is between what was done using RCP scenarios. And with regard to rainfall changes, I think in general, the rainfall changes are a lot more regionally specific. So you really have to look in you know, which country you're looking at, what season in the country, to understand the rainfall changes. So you probably can't make a general Southeast Asia statement.
All right. So, Pak Kadarsa, any follow-up from you, or we can move on? Maybe that's okay. So, okay, any more questions?
Can I
You can
ask
send.
question?
Okay, please.
Yes. Okay.
Bu Erma, please.
Yeah, sorry for not open my camera. Dr. Aurel, was your presentation is very nice and very interesting for us, and due to our global threat in Southeast Asia, it's very important to analyze the dry spell and as well as extreme precipitation also. And we also studies about the two kind of the phenomena for last decade, and found some interesting that very there is variation in spatial temporal in Indonesia actually, and based on GSMAP satellite, we found that for each region and between each region and west region also have significant difference in dry spell and also extreme precipitation in Indonesia, just for your information. And I want to ask several questions. The first one is related to your presentation about the baseline period. Do you also analyze the climatological shift? Because your baseline of the climatology is, I think, just one type, one period, maybe you have so many kind of the 30 period of the climatology, and analyze the difference for baseline period you used in your model. And the second one is related to, I mentioned before about the variation in spatial and temporal for the seasonal rainfall in Indonesia, because actually we have three types of the rainfall, and it's better to use flexibility and ability to estimate the season onset, because I see in your presentation you just separate two kind of the dry season and rainfall season by NDGFM and so on. And I think it's not enough to capture the variability of the rainfall onset in Indonesia, because we have three types of the monsoon regimes, actually, monsoonal, anti-monsoonal, and local rainfall in annual type. So it must be considered to analyze the season if we want to understand more about the regional climate variability in Indonesia. It's just my comment for your definition of the season, the simplification of the season. And the third one is related to your downscaling, dynamic downscaling. You have 8 kilometers in the western of the maritime continent in first domain, I think. In second domain. And I think it's covered the phenomena of the Borneo vortex over the South China Sea, or close to the Borneo. I want to understand, and I want to, it's my curiosity, your analysis. Yeah, I think you detail analysis for the dynamic circulation related to the Borneo vortex, because the last papers or last study about the Borneo vortex is related to climate change is weak compared to strength. It's tend to weak and seldom to occurrences of the Borneo vortex, which is skeptic for that, because the analysis break down from the global model. So maybe it's not enough to understand the very synoptical and regional scale over the South China Sea. So maybe you can also analyze the existence of the Borneo vortex from your output model in 8 kilometer in Western Maritime, if your domain can capture that. It's just a suggestion for you. I think that's all for me. Thank you very much.
Thank you, Omar. So I'll start with the so your first comment was on the dry spells characteristics and the observations, and the east-west differences and the spatial and temporal variations, and so for us, you know, your information, your local knowledge in what's going on in India, it's really valuable. We'd be happy to talk to you more about this, because what I produced here, what I showed you here, are just sort of some sort of initial, more general features that we see. So that's why we have these 2 6-season representing broad the dry and wet season in the 2 hemispheres. But I'm sure it's locally much more in much more detail necessary. So when you say that there's 3 seasons with regards to the 2 monsoons and the local, I'm sure that's the case, and it would be really interesting to discuss things further with you, to provide to get more information from you. So at this stage, we don't have any project that is dedicated to just look at Indonesia, for example. So we do need collaborators from the region to work with us on this, and to, especially like you just did, provide that local understanding from your country. When it comes to the Borneo vortex, so at this stage, the key interest in the Borneo vortex was to do with what we call the cold surges during the northeast monsoon, that once they reach the South China Sea and move towards the peninsula of Malaysia and Singapore, we know the Borneo vortex can play a pivotal role in directing and enhancing the rainfall that comes with those cold surges towards us. So we did look at that, but what we didn't look at is whether there's any historical and future trend in the strength of the vortex. So that's certainly something that we'd be interested in, and so if there's any interest on your end to work with us on this and collaborate, we would be happy to talk to you more. Thanks.
Okay, thank you very much. I'm pleasure to can collaborate with you in the future. Thank you very much, Dr. Aurel.
Yes. Thanks.
All right. Thank you, Mbak Irma. Let's move on. Any more questions from the floor? You can write on the chat box or raise a hand to ask directly to Aurel. If no, I have a lot of questions actually. So maybe one from me, Aurel.
Yes.
So I'm sure maybe you know there's a recent publication from the Codex team on their model tuning for Rexium 4. And my question is that if you look at the best performance model, they still show or some kind of wet bias on the mountainous region, like in the mountainous Sumatra and What do you think about that? How should we handle those problems?
Yeah, so I guess there's maybe two things for this. So if you have a model, say a regional climate model like RegCM or our model or whichever model it is that provides information, if you're interested in the change in the future, then look at the delta signal. That's the change. If you're interested in running local, regional, domestic impact modeling systems, you do need to investigate to bias correct your data. So, and this is what we did. So we actually produced in the process of this study a high resolution observational data set for Singapore that we used to bias correct the projections and the historical and the future, which is then useful for our stakeholders to run impact models. And so this bias correction issue is really important. We follow the EasyMap method, and EasyMap is this global effort around providing bias correction and impact data to anybody. But just to emphasize, having your own observational records in a way that you believe in it, it's being QA/QC'd, and it provides you information over a long enough period so that you can use it to bias correct your local information. I think that's really important.
Okay, thank you for the answer. We have one present, Prof. Eddie. Please go ahead, Prof.
Thank you very much, Dr. Yuda, and also for Dr. Ariel for your nice presentation. So too much information.
Yeah. Yes.
How we can okay. I have several questions. I'm sorry. Several maybe 2 years ago we no in the Jakarta is sinking also in another city, but how about Singapore sinking?
Yes.
It is also will be occur in
So
Singapore, not only Jakarta.
yeah,
What?
so I can the sinking or rising of a ground underneath a city is driven by various processes. So and they're all not related to climate. They're all related to other things. So so for example, the 2004 earthquake that was so devastating for the region, that moved tectonically some of the plates, and that was like a shock, like something happened. And then even in the decades afterwards, there's a slight coming back of it. So there's a very, very slow readjustment that happens in the background across the region in various ways. So that's one way. Then there are other earthquakes that happens every year, many times, that impact this. There's but for cities, one of the really important issues is how you manage groundwater and how you manage building your city on top of whatever ground is underneath. And I can tell you the measurements in Singapore in terms of vertical land motion is that there's very, very minimal vertical land motions in Singapore over the last 10 to 15 years. And so therefore also in our projections moving forwards, there's only a slight impact from vertical land motion on the Singapore tide gauge projections. You can see that information on our portal. So when you go into our portal to look at our results and look at sea level projections, some of the projections for the 6 tide gauges in Singapore, there's information on every single contribution. So whether it's Greenland, Antarctic, Arctic, glaciers, and vertical land motion, you can see the contribution from each of these components towards the total sea level rise in Singapore. But for this, you need to have, aside from the tide gauge information, you have to have information on vertical land motion, which means you have to have sensors in a similar location that your tide gauge is in, that looks at how the land is moving up or down. And that's important, this long-term monitoring.
Okay. What is the major contribution from land subsidence or from sea level rise? My opinion is Singapore is a small country. Maybe you can control effectively land subsidence, but for Indonesia, more than 17,000. How we can control the land subsidence?
Yeah.
Maybe it is similar question. Are you agree that more than 2,000 islands will be disappear? Several
Yeah.
years.
So thanks for the question, and so maybe there's a couple of issues mixed up here. So the land subsidence in a big city like Jakarta is a combination, or say the sea level rise in Jakarta that you're already experiencing is a combination of climate-driven sea level and non-climate driven sea level changes because of vertical land motion. And we know from publications that Jakarta has been sinking, and the key reason identified in publications is the strong extraction of groundwater at the same time building a big heavy city on top of it. So that's the key contribution for non-climate. And for climate, there were sort of several centimeters of sea level that's already happened historically. And that situation moves forward with the further warming of the oceans, where the oceans will rise even higher. So to do something against this obviously has to involve not just building coastal protection measures against sea level, but you also have to think about how you can stop the sinking, which is, a completely different thing. When you talk about disappearing islands in the future, these are disappearing islands that disappear not because of vertical land motion, because there are heavy cities on top where they're extracting groundwaters. These disappearing islands in the maritime continent or in the Pacific disappear because of the rising sea level from the ocean, future warming, because they're already very low lying. They're so low lying that even a future change of 50 centimeters will make a very significant, a devastating impact, because this 50 centimeters or 75 centimeters is only a change in the mean sea level. What comes on top is the extreme sea level and the tidal range. So what sounds like only 75 centimeters, once you add extreme sea level to it and others, you will find that for some of these low-lying islands, there'll be significant parts inundated. And that's what you talk about, the disappearing of the islands.
Yeah. I suspect maybe the position, topography and geography are also very important. Like Jakarta, it is similar with the Bangkok, Thailand. The position is like very like Bangladesh, Bangkok, Jakarta is similar position. So why Bangkok is maybe number one, not Jakarta, I think, for the sea level rise impact.
Yeah. So you remember when I showed the map on regional sea level rise? There was no station in Indonesia that I showed, because we don't have data from Indonesia, because Indonesia doesn't submit data to the PSMSL Global Archive. And therefore we don't know what actually is the information for sea level rise in Indonesia at this stage. I don't know, because we don't have the data. So that's something maybe you can do, or in Indonesia you can do, but we can't do this unless we have the information. So I can't say anything specifics, but of course, in what you mean is basically you have coastal megacities that are built near river deltas, where you have a lot of water and low-lying, or like in the Mekong River Delta or other river deltas, and you have a big city near there like Jakarta or Bangkok or other cities. And indeed, these are cities that are in danger of enhanced risk due to sea level rise and other future climate change impacts. Absolutely, and we're really interested in exploring this. So if there are groups at BRIN working in this, we would be very interested to hear about it.
Okay. Okay, maybe it is the last, yeah. If I need to choose coming from MSS, MSS means the Meteorological Service Singapore, or coming from the Assessment Report 6. What is recommendation from Assessment Report 6? Assessment Report 6 IPCC due to the Southeast Asia countries.
Yes. So
similar or different?
So first of all, our downscaling is building on IPCC AR6.
Oh.
So the global fundamental thing is IPCC AR6, and we take the models that are reported on in AR6 and pick the 6 best ones to downscale further.
Okay.
So our claim is that we provide enhanced information in time and space for the Southeast Asia region because the global models are too coarse. For example, Singapore is not on the maps on the global model because they were too small. So and similarly other maps are not. So anybody who's looked at what is called the land sea mask inside a global model, you just plot where a global model says, okay, this is land and this is ocean, and plot this over the maritime continent. It looks shockingly bad, you know, that because the islands are not resolved. There's no data points for many land places in Indonesia. So you really need to look at higher resolution. And the idea is if you pick some good quality models to do your downscaling, you actually add value beyond IPCC. You add more value because you resolve.
Mostly coming from Cordex, right? Oh.
Sorry?
Cordex.
Yes, so the key project that does this is Cordex, of course,
okay.
and we actually a member of Cordex Southeast Asia,
and we will CMAP 6.
That's right, and so but that still will take a while to see CMIP 6 and AR6 based Cordex simulations because they're still busy running them. So I think this will take a while. I think we're the first ones who have data over that domain.
But yeah, for the next time, maybe I would like to hear what the accuracy of model itself. It's very, very important. Yeah.
Yes, that's right.
So the in situ observation is very, very important.
Absolutely, and I can't stress this enough, the importance of observational data in validating and bias correcting climate change projections can't be underrated. It is absolutely important.
Yeah. Okay. Thank you very much, Dr. Aurel.
Thank you. My pleasure.
Thank you very much for your coverage.
Thank you, Prof. Eddie.
Sorry, too much
okay. No worries. We have plenty of time. So anyone for the next questions? You can write on the chat box or raise hand. Or I have some follow-up regarding that sea level question. So in your presentation, you said that the projection only done for those specific location that has tide gauge data. So you probably have mentioned it, but I missed it somewhat. Why only those locations? Not like, because you have satellites also, and you can do it also for the whole region. I'm not sure. Can you explain a bit?
Yes. So you can use the satellites to map historical sea level, and we did this. So you will find, for example, in our online visualization portal, information on historical trends in Southeast Asia on sea level. And that is a map that, you know, and you can put tide gauge locations in there and see if the tide gauge and the satellite agree. In fact, they see slightly different things, the satellite and the tide gauge. Therefore, the understanding is that the differences you see between a satellite and a tide gauge is a measure of vertical land motion. And so again, in our report, we discuss this and we show that in locations like Bangkok or Manila, where we see a clear difference between what the satellite says and what the tide gauge says, that this is the difference is driven by the additional change because of vertical land motion. So that's something. But of course, as you project forward into the future, there's no satellite data. The only information for the future comes from models. And what I try to explain is that when you want to assess sea level rise for the future at a particular place, you need to incorporate all these different processes that contribute to this, some global, some regional, some local, and put it all together. And the way IPCC decided to do this is by extracting the information from all of these different separate modeling systems and separate processes to then merge them into a merged PDF. But you can do this only at locations. So you can't do this at every grid point because you don't have that information for every grid point in the future. So you can do this only at the location where the historical tide gauge data is already there. In fact, there's even a stronger constraint. The historical tide gauge data has to be at least, I think, 20 or 30 years long. So if you only have a tide gauge for the last 10 years, you can't apply that methodology because there's not enough information there on what's already been in the history. So that's why, even though, for example, Singapore has 13 tide gauges, but only for 6 of them we were able to apply this methodology and provide future projections.
Okay, thank you for the answer. Well, all right, so anyone? Another question probably from audience? You can raise hand or write in
Can I have a question, Pak Yuda? Pak Yuda,
okay, please go ahead, Pak Heru.
Thank you very much. Thank you very much, Dr. Heru. Sorry, I have a simple question actually, but something that has been coming on for many years actually related to the climate models. People argue that actually that GCMs cannot pick up or cannot simulate the El Nino or something like that. So I wonder whether the RCMs from your results can show some or pick up the El Nino events and something like that in Indonesia, because this is quite important.
Yes, so I know what you're talking about. So this is the so-called cold tongue bias in global models when it comes to the equatorial sea surface temperatures and thereby not have the clear spatial representation of the ENSO teleconnections. That's what this relates to. You have to understand the way the downscaling happens is you have a domain. And on the outside of the domain, you have the global model keep feeding in information. And then the regional model simulating the high resolution in the middle. But the outside information comes from the global model. So the outside information also includes the sea surface temperatures, for example, in further away in the equatorial Pacific where the ENSO is active. So if you have a really bad model in terms of ENSO, then that bad modeling is being also propagated to the border inside your model. And that's why looking at teleconnections is also another assessment in picking the better models, because we do want the teleconnection from ENSO to be as realistic and as good as possible. We know they're still not perfect with the teleconnections, but we want to pick the better ones. So yes, that's what we did.
Have you been successful to get some kind of that data?
Yeah. So we see in our data that the typical Taylor connections are there. So for example, when the Singapore dry periods, when El Nino is there, or the wetter periods when El La Nina is present. So we do see the expression of these Taylor connections in our high resolution data. Yes.
Thank you very much. If it is possible to ask another question, actually,
Sure.
because
Yeah.
you have to use you have sorry, Pak Yuda, another questions. You use 2 steps in downscaling actually from the 8-kilometer domains to 2 kilometers domains, something like that, and you going to use it further for 100 meters domain, something like that, for the urban area. So why you use that kind of steps to 2 or 3 steps rather than only one go into one one step direct, for example, from the GCM direct to 2 kilometers? Is it because of the problem with the computation problem or something like that?
No, it's not a complication problem, but anybody who is doing downscaling around the world will advise you to never go from global to 2 kilometer.
Oh.
So and yes, so typically, in fact, we were usually from people who understand the downscaling technicalities. They did it before. They ask us why didn't we have another step in between at, say, 20 or 30 kilometers. So usually you use the stepwise because of the penetration of the information from the forcing data, say the global model, how far it goes inside, and then you run your own model inside, and yeah. So there's a lot of technical aspects related to these questions, but the key advice usually is you do a stepwise testing and go down.
Okay, thank you very much.
Okay, thank you, Pak Heru. We still have 5 more minutes. So anyone?
Sorry, Dr. Aurel.
Okay, it's okay.
I
Please.
think, yeah, we are very interested about the interconnection, teleconnection between IOD and El Nino. It is also very important because, but the impact, I think, not for rainfall. The standard precipitation index is more sensitive than rainfall, I think. So the next future, I think we need to investigate more about the SPI, as already you mentioned, not only in rainfall. The also combination between sea level rise and land subsidence with multi-scenario model is also very important. Not only single, but also no. We try to use another technique, another method, multi-parameter. And the other one is we need to apply the deep learning with multi model. Also very, very important to see the accuracy with precise, high quality, our model. So I think because Indonesia is too large country, more than 17,508 islands. So it is very, very, so combination between multi-technique, multi-model, multi-parameter, and multi-satellite maybe. So we can choose what is the best to get prediction for Indonesian maritime. The most very important is the tropical cyclone. The frequency now become increase and increase. Effect of global warming. Yeah, this is my opinion.
Yeah. So Singapore was never hit by a tropical cyclone, and but we do look at tropical cyclones in our data. So we started an analysis now tracking TCs and looking at the changes in the future. This study hasn't finished yet, but we will definitely try and get something published on the tropical cyclone changes, because we do get remote impact. So if there's a tropical cyclone not too far away, then there'll be impacts to our specific region as well. So I agree, you need to look at different metrics, different analytics, different data, different observations. I think to understand, there's not one truth out there. There's sort of different, even our data, we look at, say, 6 models. So we provide 6 versions of the future climate that sort of maps a certain range of how it's changing. But if somebody else does another 6 simulations of future climate, unless there's a clear reason that somebody chose faulty models or whatever, these are still also 6 future climates. And that's and so all we are saying here in CCRS is that we have this unique data set at very high resolution where you can actually look at islands. You can actually understand the changes, and the elevation is much more realistic to look across the maritime continent compared to global models.
So multi-combined atmospheric waves.
Yes.
So many complicated. Never mind. Okay, thank you, Pak Yuda. I'm sorry.
Okay, thank you, Pak Edi.
Presentation.
I think we are at time right now, and if there's no more question, maybe we can call it a day, I think. And this has been wonderful.
Yes, thank you very much, Yuda, for the opportunity to let me speak at PRIMA'sTalk. And I just wanted to repeat myself again that we are really keen to find collaborators from Indonesia who are interested in using our data, whether it's in climate, the fundamental climate science, or looking at impacts. That would be really interesting.
Right. Thank you, Dr. Aurel Mois, Deputy Director, CCRS Singapore. I'm sure there will be follow-ups from these events. You will hear from us again. And I think by this I can end the PRIMA'sTalk. I will give it back to the MC. Thank you.
Okay, we would like to thank you to Pak Yuda and Dr. Aurel Mois for bringing us a very productive session today. So, ladies and gentlemen, we are currently in the closing session. I would like to remind you that the link to the attendance report form is now available and active. Please fill the link. On behalf of the committee in charge, we would like to express our apologies that we made during the event. Thank you very much for your active participation today, and have a great day, and see you in the next PRIMA'sTalk. Wassalamualaikum warahmatullahi wabarakatuh.
Yeah, thank you, everyone.
Thank you.
Thank you, Aurel. See you next time in near future.
Izin menutup ruangan, Bapak